speakers, they are present over here. So without wasting their and our valuable time, let us start in time. Yes. अजून आतमध्ये उपस्थिती खूप कमी दिसतीये मला. चला मंडळी लवकर चला. सर कॅन वी स्टार्ट? सर करू का सुरुवात? कारण सत्कार वगैरे सो चहा घेतला सगळ्यांनी? आता तो डोळ्यावर दिसला पाहिजे. चहा घेतला तर आता सगळे मला फ्रेश दिसले पाहिजेत. गरमागरम चहा कॉफी घेऊन एक छानसा 10 मिनिटाचा विरंगुळा मनसोक्त एक छानसा ब्रेक घेऊन आपण आलेले आहात. सो पुन्हा एकदा नव्यानं स्वागत. आपण आपल्यासाठी एकदा टाळ्या देऊयात जोरदार. शेवटच्या सेशनपर्यंत जी लोक थांबलेली आहेत त्यांच्यासाठी ह्या टाळ्या आहेत. Thank you so much. So, safe and efficient use of boilers seminar organized by Joint Director of Steam Boilers, Pune. This is the first day and now we are going to start the third session. For the third session, we have the chairman, Shri UN Patil sir, Joint Director of Steam Boilers, Maharashtra State, Ahilyanagar. I request Mr. UN Patil sir to kindly please be seated on the stage as the session chairman. With your huge round of applause, we'll welcome the chairperson of this session, Shri UN Patil sir. And I request Shri Naresh Bahe, Deputy Director Pune, to felicitate, to welcome Shri UN Patil sir. जोरदार वाजू द्या, आमच्या अहिल्यानगरचे आहेत. Okay. Before we start the lecture of this session, I will kindly request Mr. G.D. Wankhede sir, Joint Director, Mumbai, to kindly please come forward and have the felicitation from us. Mr. Bhoite sir, Shri Bhoite sir, आप मंच पे आएंगे please. I request Shri Narendra Bhoite sir, Joint Director, Pune, and the organizer of this seminar to kindly felicitate Shri G.D. Wankhede sir, Joint Director, Mumbai. I kindly request Shri A.M. Junjure sir, Deputy Director, Solapur, to please come forward. Thank you, sir. I kindly request Shri S.S. Solanki, sir, Deputy Director, Mumbai, to kindly come up and have the felicitation. And I request Bhoite, sir, again to felicitate Shri S.S. Solanki, sir, Deputy Director, Mumbai. Thank you, sir, and thank you, Bhoite, sir. Yes. Thank you, sir. I kindly request Mr. Sheikh, sir, to come forward to do the honors. I request Shri M.R. Deshmukh, Deputy Director, Mumbai, to please come on the stage. Imran Mujawar sir to please be on the stage, Deputy Director, Mumbai, and I request Sheikh sir to do the honors. Shri Naresh Bahe sir to come forward to do the honors. And I kindly request Mr. S.A. Razurkar sir, Deputy Director, Nashik, to come up on the stage. I kindly request Shri A.D. Khobragade sir, Deputy Director, Kolhapur, kindly come up on the stage, and Bahe sir will do the honors. Thank you. Thank you so much. And now, here we go with the third session, first lecture. I will humbly request Mr. Narpendra Singh Ji to be on the stage. Please put your hands together for our esteemed speaker, Mr. Narpendra Singh Ji from IncoSTEM International Private Limited. He is CEO over there, and his expertise is STEAM equipments. Today he is delivering his Power Pack lecture on steam system efficiency enhancement for process boiler plants. So, please.
Good evening, ladies and gentlemen. First of all, I would like to thank Steam Directorate of Boilers for having these sessions, which are so beautiful, so lovely, so insightful, and so knowledgeable. I saw the presence at Solapur. There it was full packed, jam packed. It is same here, and I think these sessions are very, very important. Congrats to the entire team for getting these done. Great job, sir. So I will come to my session now, which is on steam system efficiency enhancement for process boilers. There is a saying that these sort of sessions have much more value when these sessions become more interactive. So I would love to have any questions in between, and I would be very, very happy to answer those in between. Let's have these sessions as more interactive as we go along. Any sort of questions, any doubts, you can ask me, interrupt me in between, so that we can have this session as more very, very interactive session. So steam, we are all talking about steam from the morning. Steam is the backbone of industry, which is used for all industries. Why? Because it is very easy to make through boilers. Water is easily available. Steam is generated through various fuels, like we can use oil, we can use biogas, biofuels, and we also heard about hydrogen as the upcoming fuels. It is very efficient and easy to generate. It can carry very large amount of energy in very small pipes. And there are so many, it follows, the most important is, it follows a unique temperature and pressure curve by which we can easily control it for our all processes, however complex they may be. Steam has been used for ages. I will show you one engine. Like this is the earliest usage of steam has been, the first usage of steam was in coal mines, where the coal industry was is long ago, when they have a peculiar problem of water coming into the coal mines. For removing that water, steam was used, and these were the engines developed at that particular time for taking out the steam. for taking out the water from the coal mines. And that was the first industrial use of steam. And now we can see that for all the industries, like chemical plant, pharmaceutical, paper, food and beverages, rubber, you can name any industry, power, everywhere we use steam. It started from coal, and now we are seeing that it's everywhere. And why this session is so apt now, today, is because if you look at all industries, we can see the manufacturing cost of steam is very, very high. Means for the entire, so for example, like for any chemical plant, it can go up till like 20% of the manufacturing cost of a chemical, including the raw material. So it's so important for us to efficient use of steam becomes so very important, because we can see nothing is less than 10%. So it is, as paper and pulp is 35%, 30%, pharmaceutical is 25%. So 25% of the entire manufacturing cost is the steam cost only. If you talk about steam, like these are the 4 pillars by which, like boiler house, steam distribution network, steam usage at the process plant, and condensate and flash steam recovery. These are the 4 basic areas where this thing. Now I will show it to you through a graph. The topmost portion, if you look at 100%, that is the total energy a fuel is giving for generating the steam, like 100%. And we have losses at each and every section. Like the boiler house, after the boiler, okay, 85%. After distribution, it becomes 75%. After utilization, it becomes 60%. And then we do certain recoveries, after which it's 65. This is what it is today for different industries. Average industry, what I'm talking about is average industries. This is a typical pattern which the industries follow. There is a loss at every stage. So at the end of the session, I will show you how we can optimize this, and I will show you at the end of the session the graph which we can follow after optimizing, what is the total benefits we can reap out of this optimization. Any doubts still here? Okay, great. Okay, if we talk about boiler house, there are different things like stack loss. This session was very nicely covered with our friends from Force Marshal. Excess air, poor O2 control, again, it was the same thing. Blowdown loss, radiation and convection loss, poor feed water heating, quality of steam, which is generally not spoken about. We always talk about efficiency of the boiler. We many times miss about talking about quality of steam getting out of the boiler. Air preheating. These are few of the things which for a process boilers are important to monitor each one of them. We'll see in between. If we talk about excess air, it is for different boilers. We are seeing it's a graph which is self-explanatory, and what is the efficiency gain out of this? How much we can gain out of it is also given here. And for typical fuels, what would be the ideal oxygen levels we can get from different fuels? Like for coal, FO, natural gas, biomass, what is the percentage at which we can operate and get to a ideal combustion level, which in the previous sessions we spoke about, we saw what would be the ideal combustion levels by which we can get the maximum efficiency. So for any fuel, we can see what is the, for our boiler, which fuel we are using, and we can monitor it accordingly. Importance of drum level control, what we talk about quality of steam. Quality of steam actually is very, very important. And for process boilers, when we are talking about this session is specifically about process boilers. We talk about, because the process boilers, the operations are such, it is start and stop. They have batch times. So this becomes very, very important. If you talk about process boilers, the another thing is the difference between the peak load and the low loads. That also varies. Most of the process boiler today are like single element control, where by the Mowbray we are operating the pumps. But what we talk about with a, okay, with a three-element control system is boiler drum level control, which we all do, boiler feed water flow rate, and steam flow rate. This is so important because whenever our peak loads, whenever there is a sudden surge of demand from the plant, there is a tendency of water carryover. How we can reduce it, how we can actually foresee it earlier, and ensure that our systems are integrated in such a manner that these problems don't arise. Why this is important? I will go back to this old slide. Here, the orange one is the steam quality. The graph, orange graph is the steam quality graph. And blue is the process efficiency or the thermal efficiency of your process equipments. For any plant, take any pharma, take a paper, take textile, every plant, blue is the thermal efficiency of each and every of your equipment. The thermal efficiency of your equipment is directly proportional, almost directly proportional to the steam quality. Here we can easily see, as our steam quality improves, our thermal efficiency of our plant, entire plant is improving. So it's so important that we have a good quality of steam, and when we talk about good quality of steam, your water carryover from the boiler should be at the minimum, even with varying loads. If it is a constant load, it is easy to maintain it. But when it comes with varying load where the highs are high and peak lows are low, and with certain fluctuations, there this three-element plays a very, very important role, and it can ensure that you're still, even with peak loads and low loads, you still have a good quality of steam coming out of the boiler. Any questions on this? Okay. And how? I've given a small this thing. Here we see like as the moisture in the steam increases, our thermal efficiency or the latent heat reduces in the graph shown below. Here we can also see the efficiency gains and with a 90% steam quality and with a 100% steam quality, we have 4 to 5% efficiency gain from our system. And if we talk about rupees for a 10-ton boiler, we can see like 54 lakhs per year if you improve the quality of the steam. And again, we spoke about three-element control system, handle sudden load, better level stability, improved boiler safety, faster response to load variations, and so on. Again, this is also very, very important. We have seen that so many process boilers are there below 10 tons, where there are 4-ton boiler, 6-ton boiler, 10-ton boiler. Their feed water arrangements are not properly designed. We talk about starting with the feed water tank size, how we are controlling it, how we spoke also about automation. Antapurka sir was speaking about we have certain automations in place, and why? Because these things help. If you have a proper automation in feed water management system also, we have huge opportunities of improvement. As we have seen that every 6-degree rise in our feed water temperature can ensure we have 1% saving in fuel. So very important for us to have good feed water control or I would say more than good feed water control, but optimized feed water control is very, very important. Here again, I have tried to make certain pictorial slides for easy understanding. If you have good feed water control, your fuel consumption reduces, you have improved steam quality, minimized blowdown losses, and of course, the equipment life increases. Now we talk about air preheater, which I think many people must be using. Very simple, like every 18 degrees rise in feed water, air fed into the boilers will improve your efficiency by about 1%. So in pictorial form also has shown how the combustion air temperature, when increased, you have efficiency improvement of the boiler. So very, very easy slides to understand, and I've tried to put it in annual savings as well. So improves boiler efficiency, reduces fuel consumption, improves combustion control also. and most importantly is reduces emission. Now, more and more we will be on not only talking about efficiency but also of emission control and increase the generation capacity. No sooner the boiler efficiency improves, your total steam generation capacity improves. And shorter startup times. Then on the boiler side, I think the last one is the control on the TDS. Okay, these are the few things by which the foaming and bubbling happens and your TDS comes up. We have side blowdown, we have bottom blowdowns. Why this is important to control? Again, through a graph I will show. The lower graph, if we see, is something where our TDS level in the boiler increases and we do a blowdown once in a shift. You can see a straight drop of the TDS levels. Your boiler continuously, the TDS level increases and suddenly there is a drop. So we are doing it every shift. Mostly it happens like that. And if we automate it through small automation, we will have the above graph, which shows we have shorter blowdowns done for a quick time, 10 seconds, 15 seconds, and we maintain the entire TDS in a very, very small band. First of all, it will be very good for the safety of the boiler, and you will also optimize on the overall blowdown total efficiency. You will have lesser of blowdown, and or maybe more importantly, you will have optimized blowdown with this. Any questions on this? Okay, great. So benefit of automatic blowdown. Again, I have written like the water savings, maintenance. Of course, if your blowdown increases, you have maintenance issues also coming up, and you have fuel savings as well. Because generally anything between 4 to 5% we have blowdown losses, but we can optimize that by keeping the band low. Again, now I'm coming to the boiler house is complete. We have spoken about all the different elements which actually have an impact on the efficiency of the boiler house. Now we talk about steam distribution network. It is so important, like once we have, if you remember the first graph, the boiler losses were only 15%, but the distribution losses were about 20%, which is more than the boiler house. Many people talk about boiler house, but distribution also plays a very, very important role. Proper streamline sizing design, where we maintain the proper velocities while designing our streamlines. What if our steam is saturated? What if our steam is superheated? We have to take different things into account. Like for superheated, we take about 50 meters per second, which is okay. But for saturated, we should not go above like 25 to 30 meters per second. So those things are there while designing a streamline. Good engineering practices also play a very, very important role, how we take the droppings from a main line and all that stuff. Pressure drops to be taken into consideration while designing the systems, again, very important. Proper condensate evacuations at periodic intervals from the streamlines, and insulations also play a very important role. Again, these same points. The streamlines should neither be too big or not too small also. Both have their impact. If the streamlines are low, then what will happen? Steam starvation. What if they are big? The velocities will be much lower and you will have a lot of condensation happening. Again, when we put up a project, we talk about like putting different lines. I will show you an impact, like if we are using a 4-inch line instead of a 3-inch line. We have 20% more radiation losses. But sometimes we do. While designing, okay, we have like 5-ton load, okay, we provide extra safety, okay, 7 tons kar dete hai. We go for oversized lines. What happens is, you are losing on 20% radiation losses forever till the plant is there. each second, each hour, each day. So it's very important to stick to the designed philosophy and to the points. Okay, this I covered. And good engineering practices to be followed for ensuring good quality of steam at the end of the process. Ultimately, steam is getting generated by the boiler, you are distributing it, but you are doing the process at the process. So ultimately, what happens, what matters is the quality of steam reaching the process is what that matters, is what your efficiency of your entire plant will depend upon that. So the entire lining, steam lines which are like somewhere it is 500 meters, somewhere it is 1 kilometers from the boiler house to the plant is very, very important to have to ensure that the quality of steam does not deteriorate from the time it reaches it leaves the boiler house till it reaches your equipment. It should remain the same. For that, you have to ensure that you have proper evacuation of the condensate from the main lines, no water hammering, and all that stuff. You have proper gradients of steam lines to be followed. If you follow that, then we have a good quality of steam reaching our process. Otherwise, your quality of steam will deteriorate, your quality of the process will deteriorate, the efficiency of the process will deteriorate. Okay, these are few examples how good engineering practices are to be followed. Very, very simple ones, where how you have a gradient of 1:100 while putting the line. You have traps after every 30 to 50 meters, depending upon the quality of steam which is there. For superheated steam, it can be 50 meters. For saturated steam, it can be 30 meters. How you take the steam lines always from the top. These are very, very small things, but people make a mistakes there in the plants, and then deterioration happens. How we take out the condensate from the main line, you can see on the right-hand side, top corner. These are important points, but good engineering practices should be followed, otherwise you will have deterioration at the end of the line. So again, contaminated steam reaching the process is there. Scaling, rusting over a period of time. You have strainers, moisture separators put on the line, which is important. Will not go into much details of it. Now come to proper steam trapping. When we talk about proper steam trapping, first I will talk about main steam lines. We have which traps to be used are very important. When we talk about the main lines, ideally thermodynamic traps should be used for the main steam line. Again, we have seen in Indian industry that we have been using steam thermodynamic trap. Every company must be using it for so many ages. Still, we have a lot of problems in that. And I would say anybody can pick up the hand who says that my 100% of the traps are working fine. I don't think there would be many. Can anybody pick up the hand and say? No. Everybody has some or the other problem? Yes or no? Yes. Okay. So it's like none of the user's problem. Ultimately, it's how we are designing the system. These traps have been designed so many ages ago, and we have been using the same philosophy from then onwards. What happens is these thermodynamic traps they fail. Fail why? Because of air locking happens. What do we do after that? Yeah, he's right. We hammer that. जोर से बोलो. क्या करते हो? We need to hammer it. Everybody has been taught this from ages, but nobody has come out with a solution for that. ये बताया, we know the problem, and we know the solution also, and we have told the solution, but nobody has worked on the root cause. And I'm proud to say that we at EncoSteam, we are the first company in India who have developed thermodynamic trap with air venting facility. Herein, there is a bimetallic ring by which any bimetallic ring senses the difference between the air and steam. And whenever air comes, it opens the trap, venting happens. So there is no air locking, no need of hammering, which we have been doing for last 70 years, from the time these thermodynamic traps have. So let's go to the good technology, latest technology, and ensure that 100% of our traps work. Otherwise, your quality of stream at the end of the process is a problem. So, again, this is something about insulation, which I will show it to you with this figure. Insulation is also so important on the main lines that it plays a very important role, again, with respect to the quality of the stream and with respect to radiation losses also. We can see that a temperature of, if any, like 35% more heat losses happens if our temperature rises from 3 bar to 8 bar. If we talk about stream pressures, if it increases from 3 bar to 8 bar, with a good insulation also, we have our heat loss from 51 watt per meter to 69 watt per meter, about 35% losses are there. So it's very important to keep our insulations intact. Do regular checks and audits for our insulation. Otherwise, you will lose 24 hours a day, 365 days a year. What are simple checks for checking the insulation? Any say? It's as simple. 15 degrees more than the ambient temperature should be your insulation temperature. If you check the insulation temperature, it should not exceed 15 degrees more than the ambient temperature. If you keep it below that, your insulation is intact and your insulation is good. And you will have not these losses. Otherwise, you have huge losses. Any point on this? Or questions? Good. Great. And again, I have shown like the potential savings are 25 to 40% with these good insulations. And I have shown with surface temperature of 45 degrees and 65 degrees what the losses can be there. Then, again, the utilization, now I am coming to the process. Now distribution network has been completed. I am coming to the process at the point of use. At the point of use, we need to ensure that our processes are run at optimized pressures, steam pressure. Our pressure should not be more or should not be less. These have to be optimized. Very, very important. Poor condensation drainage, air venting through the steam system, which I will cover in slight detail. So why, when I am saying that pressure profiles are so important, we can see difference in latent heat is 86 kilojoule per kg between 3 bar and 7 bar. Means latent heat at 3 bar is, latent heat at 3 bar, which is, here you can see like 300, is 2133, and at 7 bar is 2047. So it was about 4.2%. Means you will save about 4.2% of your steam by reducing the pressure. Here I have shown a pictorial form, 1 bar, if you are using 1 bar stream, 3 bar, 5 bar and 8 bar, what could be the savings you could achieve? And these are phenomenal savings when we are talking about each and every equipment of your plant and we optimize the pressure profiles of the plant. It's huge savings. If you can do a process at about 3 bar instead of 8 bar, you are saving how much? 7%. You can see there. 3 bar and 8 bar is 7% you can save. So that's why we use PRS stations, pressure reducing station. Everybody uses it and for the process. Why? Without PRS, when we are overheating, you have so much of steam which is transferred without transferring its latent heat. So your latent heat is not transferable and you lose on that. And with proper optimization, you have optimized heat transfer and save on so much. So these are pressure reducing stations, which I will not cover in detail because everybody must be knowing it and using it. Now come to process trapping. When we talk about previously we spoke about mainline trapping, now we are talking about process trapping. Generally, process trapping, if we talk about process trapping, we have ball float traps, we have thermostatic traps, we have bimetallic, we have clean steam traps. If I talk about ball float traps are most widely used for all the process applications. Any industry, this thing, we use ball float trap. Thermostatic traps are basically used for tracing applications. For tracing line applications, we have big refineries where there are kilometers of piping. And where there, the entire fluid which is flowing has to be kept at a particular temperature. And at those places, we use thermostatic traps. When we talk about bimetallic traps, bimetallic comes in the play where float traps and thermodynamic traps cannot function. The temperatures are so high. Then these bimetallic traps come into play. And finally, the clean steam traps. Clean steam traps are very specifically used for pharma industries and bio industries. When we speak about clean steam traps, there are three different criteria for it. First is, it has to be made out of 316L material. All traps are designed for 316L material. The design of the trap is such that the drainability, it is self-drainable. Means the drainability has to be, there should not be accumulation of any condensate. Otherwise, there will be a bacteria formation, which is not good. And then the surface roughness inside the trap should be less than 0.4 Ra. And finally, all the traps have to be ENP plated, electroless nickel plated. These are the four criteria for any clean steam trap. So these are different traps for the process applications. We spoke about thermodynamic trap for the mainline leaking. What about process traps? If process traps leak, what happens? Huge losses to the plant. When we talk about, I have given an example there. At 2 bar, at 2 bar, if a 1-inch trap fails, then we have about 5 lakhs of one trap, one single trap, we have 5 lakhs rupees per year. Similarly, at 6 bar, it will be 27 lakhs. One single trap can drain you this much amount of money. And imagine the number of traps and the traps leaking, how much you can save in your plant. This is a simple, I have used pictorial slide for your easy understanding, and any 10 bar, any 10 TPH plant would have about 100 traps, process traps. And if we ensure that the traps are working fine, we will ensure that we have reduced our leakages and improved our system efficiency. Any points still here? I think there should be many questions. Nobody is asking. Okay. How those figures come up? This is a simple graph which shows as the steam pressure increases. Here I told at a 2 bar you have 5 lakh saving. For 6 bar it is 27 lakhs. Why? As you see the pressure increases, for same orifice your leakages increases. And increases in a parabolic form. So, very essential to ensure that our traps are operating in the right manner. This is the graph which shows, like for example, a 5 bar 10 mm orifice trap would leak about 170, this particular line. 5 bar going up till orange line is about 170. 170 kgs of steam per hour. That much it will lose. Okay, great. Oh, sorry, I'll just try to finish it fast. Then these are ball float traps, a simple little thing designed with a complete module. Now you don't have to fabricate by putting a strainer separately, NRV separately, valve separately. You can get these modules. Sorry. Now, coming to the one more very important this thing is air. air venting. When we are talk about process boiler where you have a lot of feed water coming in, fresh water coming in, you have lots of starts and stops, because you have all batch processes, air will come into your system. Air will come into your systems, into your steam cycle. Air has to be removed from the steam. Otherwise, air is a poor conductor of heat and it will reduce your thermal efficiency of your equipments. How? If you see this graph, the red side is the steam side, the blue side is your process side. And you have your heat exchanger, which is a metal wall. If you have an air, which is shown in yellow, you see the temperature drop it can create. It can create a huge drop. From my calculations which I have done is air is even worse than condensate. It is more dangerous than condensate into the streamline. So you can see the drop and it will, what it will impact your entire equipments. Thermal efficiency of heat transfer. It will impact thermal efficiency of heat transfer. So what do? We have these air vents by which air vent have to be put on the top point of your equipment on the steam lines, on the topmost point, because generally the air reaches at the top point and from there it can be released. These work on principle of what we call it a thermostatic capsule by which it senses between air and steam with respect to the temperature. Again, a reaction in a chemical vessel which we did certain exercise, it can save you like 15 to 30 lakhs per year by ensuring that you don't have air into your system. As high as that, by installing air vents. So very important, and this is one particular thing which is totally missing in most of the plants which are already set up. Now the new plants, all the consultants are ensuring that the air vents are put onto equipments, and the OEMs who are supplying the equipments are also putting the automated air vents. Otherwise, all the old plants don't have it. And so, but it's so important to have these sort of this thing. So, okay, coming fast because we have a couple of minutes more. So, flash steam generation. We have crossed the process side. Our equipment's efficiency we spoke about. Now the recovery part, which is the flash steam and the condensate. Again, if we talk about a 10 bar steam which many plants use, how much flash steam it will generate out of the equipments? If you go up from the 10 bar to the first line, which is if it is exposed to atmosphere, it comes to about 16%. So 16% of flash steam will get generated. And generally, we see that it comes out of the, where you see, it comes out of your vent tanks, यहाँ पे condensate return, where the condensate return is coming up, it's coming out of this. Patel साहब correct? वो पूरा tank में से आता है. So this is what is very important for us to save the flash steam. Again, with pictorial form, I have put how much savings you can achieve by ensuring that you recover all the flash steam. Flash steam will get generated. The process is such, it will get generated. But you need to ensure that we recover that flash steam. Once you recover that, you put it to good use. Lastly, condensate recovery system. By recovering the condensate, what will happen? Condensate itself has a lot of heat. The blue line is the total energy of steam, but the red line also shows the energy in the condensate, which is coming out of the equipments. So we have about 20 to 30% of the percentage of energy which the condensate has as compared to steam. So it is equally important for us to recover the condensate. Apart from recovering the condensate, we save on water, but you also save on the steam, which is about 20 to 30% of the total steam, this thing. So very important for us to recover the condensate as well. Now this is the final slide. The first slide which I showed for the process was the blue line, how we were there with respect to the losses. This is In general, most of the process plant follow that blue line today, maybe some ups and downs. And orange is the line by which we can save after optimization. So the total saving can be as high as from 85 to 65, 20%. Means you can reduce your steam cost by how much? 20%. Means that much. After optimizing these things. So this was my life side. Thank you.
Thank you, sir.
Any
query,
questions?
any doubt
Yes,
from
please.
anyone? We'll provide the cordless. Please provide it. त्यांना माईक द्या. नाही तुमचा नाही, ते देतील ना. तिकडनं माईक द्या ना एक.
My question is
Yes, sir.
related to auto blowdown system.
Okay.
Can you please explain actually how this system works?
See how generally when the boiler continuously produces steam, steam is nothing but pure water. It gets evaporated and converts into steam and goes away. What the residue, which is calcium carbonate, calcium bicarbonate, magnesium bicarbonate, there are so many impurities into the water, which remains there. And it increases the TDS level as a period of time. As we go along, the TDS level will keep on increasing. So we have to remove that. Traditional method, we do the blowdown once in a shift, correct? Yeah. In automatic blowdown system, what it does is, you have a sensor which senses the TDS level. You take a surge after every 15 minutes, after every 30 minutes, whatever time you set. You take a surge, and when it passes through that sensor, it will check the TDS level. And you have a defined range at which it will be set. If it goes above that range, you will have a blowdown cycle. And that's how it works.
Okay. Thank you.
Hope I have answered your question.
Yes. Thank you, sir. Thank you.
Okay. Any more?
No, it's okay. Okay.
Thank you.
I request Shri UN Patil sir to kindly come forward to felicitate Mr. Narpendra Singh ji.
Thank you, Narpenji. You have explained very good manner. We know the boiler, how to generate the steam we know. You have explained that how to properly utilize the boiler and how to maintain the quality of the steam and how to optimize the boiler efficiency. And you have explained that techno-commercial manner so that you can show these sheets to your management also. So they will focus on the equipments which can save the loss which is going waste. So thank you very much.
Thank you, sir. Thank you. Thank you. Thank you, Narpendra ji. And as we are here to end up today's session with a very, very important topic, that is why supercritical boilers. And for the same, we have a very experienced personality with us. We have the speaker, Shri G.T. Chaugule sir, ex-joint director of boilers. Please put your hands together for Mr. G.T. Chaugule sir. He is having more than 29 years of experience. He is BE Mechanical and he has done diplomas in business management, labor laws, human rights, and intellectual property law. He has acquired MBA HR, an LLM in business and LLM in criminal law, and now he is pursuing his PhD law. So I kindly request Mr. G.T. Chowgule to deliver his lecture on why supercritical boilers. So.
सर्वप्रथम माझा नमस्कार सगळ्यांना. आता वेळ तर भरपूर झालेला आहे आणि टॉपिकसुद्धा असा आहे की थोडा समजायलाही अवघड आहे, परंतु आपण अशा पद्धतीनं समजून घेऊ की ती सगळ्यांना समजेल. सर्वप्रथम मी पुणे डिव्हिजनचा आभारी आहे की त्यांनी मला इथं अशा टॉपिकवर लेक्चर देण्यासाठी बोलवलेलं आहे. तर मित्रांनो, पहिल्यांदा आपल्याला वाय सुपर क्रिटिकल बॉयलर आणि ही जी टेक्नॉलॉजी आहे ती टेक्नॉलॉजी आपल्याला समजून घ्यायची. ती समजण्यापूर्वी आपल्याला एक थोडंसं रिव्हिजन आहे. ते रिव्हिजन म्हणजे की व्हॉट इज द क्लासिफिकेशन ऑफ बॉयलर्स. बॉयलरचं क्लासिफिकेशन काय आहे हे पहिलं समजलं पाहिजे आपल्याला. तर बॉयलर्स आर क्लासिफाईड ऑन डिफरंट वेज. ॲज यू नो, वी आर फॅमिलियर विथ दी smoke tube boiler and water tube boiler, which is day to day in use. The classification is based whether the smoke flows through the tube or water flows through the tube. This is one classification. The second classification is based on end use. That means where the boiler is used, whether it is used in industrial purpose, whether it is used in utility purpose, or whether it is used in marine, or whether it is used in even nuclear power station. So this is that classification. Then depending on the firing, we say our boiler is stoker fired. Sometimes it is pile firing also, that is dumping rate we say in our language. And firing may be CFBC, AFBC, like that. Even liquor fired boilers are also there. So this is the classification on firing basis. Then operating pressure. So operating pressure, regarding the operating pressure, there is a lot of confusion. Some of us say कि it is a low pressure boiler, medium pressure boiler, high pressure boiler. But what exactly is the demarcation? That we have to classify now. And in this classification, basically, there are two types of boilers, subcritical and supercritical. Now the question arises, कि when we say it is a subcritical, सबक्रिटिकल केव्हा म्हणायचं? मराठी चालतं ना सगळ्यांना? सबक्रिटिकल केव्हा म्हणायचं? 2 टनाचा बॉयलर आहे, 10 kg आहे, 20 टनाचा आहे, 45 kg आहे, ही एक्झॅक्टली काय आहे? इज इट सबक्रिटिकल? येस, डेफिनेटली, बिकॉज देर इज अ क्लासिफिकेशन. In water, you see there is a critical point. That point is 221 bar and 374 degrees centigrade saturation temperature, corresponding to that 221 bar. So that is the point, and the boilers which are working below those point, that point, temperature and pressure, are called the subcritical boilers. And above that, they are called the supercritical boilers. So this is, in this topic, why supercritical boilers, now we'll come to the information regarding की supercritical boilers. Now सबक्रिटिकल कशाला म्हणायचं मग 2 टनाचा 10 केजीचा असेल तरी तो सुपरक्रिटिकल झाला. 45 केजी 45 टनाचा असेल तरी तो सबक्रिटिकल झाला. सो दॅट इज दी डिमार्केशन. नाउ देर इज फर्दर टेक्नॉलॉजी अबाव दॅट पॉइंट, दॅट इज 221 बार and 374 degree centigrade. Above that is called the ultra supercritical. Now those boilers which are running at 250 bar pressure and temperature will be 565, 570 or even more that up to 620. The present technology of power boilers was up to 620 degrees centigrade design temperature. Now these supercritical boilers and ultra supercritical boilers nowadays they are working at about 650 even 670 degrees centigrade. That is metallurgical restriction. And above that also there are boilers which are working at 750 degrees centigrade design temperature. And the working pressure is about 400 bars. We cannot imagine that, but still they are running. So this technology, why? That answer you will come to know later on. Now the classification next is based on draught. Natural draught boilers, forced draught, induced draught and balanced draught. Then based on circulation, that is natural circulation, that is drum type boilers. Now the drum type boilers, you know, there are 2 drums. The next classification in that circulation is the forced circulation. In the forced circulation, these supercritical boilers work. Next classification is based on construction. Construction means whether it is a package boiler, whether it is a field directed boiler. Then next classification is based on type of support. Whether the boiler is bottom supported, whether it is top supported, or whether it is a middle supported. If the middle supported boiler is there, below the middle point, the expansion is towards the below and the top portion expands upward. Then based on furnace construction. Furnace construction means whether the boiler is single pass, whether it is a 2 pass or 1.5 pass. So this is the classification of boilers. So basically we should understand कि depending on the classification, कि how the classification is made. Now the next point is specification. Most of the times we come across कि what is the specification of the boiler. Now the specification of the boiler is basically done on 4 points. That is steam flow rate, that is evaporation capacity, which is measured in ton per hour. The second point is steam outlet pressure. What is the pressure for that boiler? Then steam outlet temperature. And third important point is feed water inlet temperature. Now in these feed water inlet temperatures, there are 5 things. 5 गोष्टी महत्त्वाच्या आहेत की those boilers which are working without deaerator, they are having feed water temperature in the range of 85 degree, 90 degree centigrade. The second classification is with deaerator, where the deaerator temperature is 105 degree centigrade and the pressure inside the deaerator is almost about 1 kg per centimeter square. Then the third category is without heaters. The feed water temperature can be in the range of 130 degree centigrade to 140 degree centigrade. Then next classification, that is fourth classification, is with HP heaters. And those HP heaters may be inline. Inline means that is called regenerative feed heaters. Those are also called cascade type of feed water heating. Now the last and the fifth category of feed water inlet temperature, it is related with the HRSG, heat recovery steam generators. Those boilers are, you know it, they are working with the combined cycle, gas turbine and steam turbine. So there the feed water temperature is in the range of only 30 to 40 degrees centigrade. And that is again heated in preheating. So this classification of feed water is very important as considered to the efficiency of the boiler. Now we will come to the scenario, what is the growth of power unit sizes in India. In India, in the year 1965, the boiler capacity, unit capacity was about 60 to 75 megawatt generation capacity. Then slowly there was a development again. In the 1966 again immediately, the power boilers were about 100 and 120 megawatt. Then next to that, this 200 to 10 megawatt technology came. That is in the year 1972. Then in 1991, this 250 megawatt that was introduced. And afterward in 1979, that means in between 1972 and 1991, 1979 there was 500 megawatt. The first 500 megawatt boiler was erected in India at Tata Power, Mahul, Trombay. This was BHL make. Then next, in 2004, 660 megawatt technology has come up. That is supercritical technology. Actually, this technology started in India during that period, 2004. Then in 2008, successively after that, the 800 megawatt unit has come up. The first 800 megawatt unit in India was erected in Mundra, near Kutch. Mundra port. It's a very power complex there, more than 4,000 megawatt at a single place. So this is the scenario. Now after this, you see 800 megawatt unit, single unit. Then you can imagine the capacity of that boiler, that is TPH capacity, evaporation capacity. Those boilers, they are working up to 620 degrees centigrade temperature. Then afterwards, 800 megawatt, the present situation is 1000 megawatt single unit. This is in operation. So this was the scenario in India. Now we will come to the technology. What is this technology? Now, what is supercritical pressure? That already I have discussed regarding that. The critical point in water vapor cycle is the thermodynamic state, where there is no clear distinction between liquid and gaseous state of water. Water reaches to this state at a critical pressure about 221 bar and 374 degrees centigrade. So this is the definition of the supercritical technology. Now, why we are coming to this technology? You see, drum pressure till now, the boilers were operating up to 200 megawatt, 200 bar and less than that also. And superheater and reheater temperatures were up to 540, 565 degrees centigrade. Now this was the limitation. Why? Why it has come? You see, because as the pressure increases, the density difference will come together near to that. And this is the reason this subcritical technology has to stop there and there only. Then only, till now, in between 200 bar and 221 bar, there are certain units which are operating under assisted circulation. Assisted circulation, that means they have to provide one additional pump also. But it is a very rare, that operation is very rare. Now the limits of natural circulation. Due to density difference, there are limitations of natural circulation. Then plant thermal efficiency, till now we get up to 35% in subcritical boilers, that is power boilers. Then fuel consumption was also increased as compared to supercritical technology. Then CO2, SOx, NOx emissions were more. Then performance of environmental impact was also more. Then limit of flue gas exit temperature and unburnt losses were also more. And this has given the next improvement, which is supercritical condition. Now, higher steam conditions increase overall steam cycle efficiency. Adoption of supercritical technology is a major step, and it involves extensive changes in piping, controls, and auxiliaries also. So this is the requirement. Sorry. Now, natural circulation versus once through system. In this figure, you will come to know clearly that subcritical boilers operate on this figure, left-hand side figure, and on right-hand side, you see the supercritical boilers operate. But in this case, in supercritical boilers, there is a vertical tank that has shown, and even supercritical boilers operate as subcritical boilers up to 30% load. And that operation is called the weight operation of the supercritical boilers, as good as subcritical boilers. Now afterwards that, it goes to the supercritical mode of operation, that is also called the dry mode of operation. Now we will come to know cycles. Temperature entropy diagram of subcritical. Now this is subcritical cycle. 1, 2, 3, 4, 5, 6, 7, 8, 9 again is a subcritical cycle. And critical point that is shown there. And this is the supercritical cycle, that is A, B, C, D, E, F, G, H, I, A. So this is the difference. Now Rankine cycle for subcritical unit. That 0.12 CEP, that is condensate extraction pump work. Then 2, 3 LP heating, 3, 4 boiler feed pump work, 4, 5 HP heating, 5, 6 economizer water wall, 6, 7 superheating, 7, 8 HPT work, 8, 9 reheating, 9, 10 IPT work, 10, 11 LPT work, and 11, 1 is the condensing. that is the heat rejection. Now Rankine cycle for supercritical units. That is 1-2 is a condensate extraction pump work. 2-2s is regeneration. Then 2s3 boiler superheating, 3-4 HPT expansion. 4-5 is reheating, 5-6 IPT, LPT expansion. 6-1 is a condenser heat rejection. So this is the difference of supercritical Rankine cycle and subcritical Rankine cycle. Now we will come to the point, that is variation of latent heat with pressure. How the latent heat varies as the pressure increases. You can see that absolute pressure increases from 50 bar to 21 bar. And saturation temperature, that also increases from 264 to 374 degrees centigrade. And latent heat is from 60 to 40, that becomes 0 at 221 bar. And this is that technology which works above this. Now important phenomena in this technology is very important, that is departure from nucleate boiling. First of all, we must understand, even in subcritical boilers, what type of boiling is taking place in the tubes. There are two types of boiling, that is film boiling and nucleate boiling. So which is prepared then? Now this nucleate boiling is a type of boiling that takes place when the surface temperature is hotter than the saturated fluid temperature by a certain amount, but where heat flux is below the critical heat flux. Then nucleate boiling occurs when the surface temperature is higher than the saturation temperature by between 4 degree to 30 degrees centigrade. That means in that range of temperature, overheat takes place. Now you see the graphs density versus pressure. As the pressure increases, so this density of steam and density of water equals. And correspondingly, this deviation from nucleate boiling occurs when the temperature difference between fluid and turbulence and heat transfer rate, that particular point. And that point is called DNB. So there should not be departure from nucleate boiling when the boiler is in operation. Now, what is the construction of the supercritical boiler tubes, water tubes? Two types of tubes are used. On left hand side, you see those are called the rifle tubes. And on the other side, you observe that they are the plain tubes. Then which is better? For these supercritical boilers, to have a control on mass flow rate, these tubes are designed for that. Those tubes are called the rifle tubes. Now the minimum mass flow velocity in the plain tubes is more as compared to the minimum mass velocity of the rifle tubes. So this type of construction is there. Now you will see in the next figure how the boiler is constructed. The bottom portion of the furnace is constructed by means of rifle tubes. And the construction is in such a way that the bottom headers on all sides, 4 sides, and from the bottom headers, if you start one tube from one point, it is inclined at 30 degrees centigrade, and at every level, that angle is followed, and it is completed at the top header. So, bottom half portion of the boiler is constructed of rifle tubes, then collected portion of the fluid is collected at the middle headers, and from there onwards these plain tubes are constructed. Because If we construct only plain tubes, the height of the boiler will be tremendously increased. So to reduce that, these type of rifle tubes are used. Now you will see here how the boiler works. The economizer phase number 1, 283 degrees centigrade. Then economizer phase number 2, 2 economizers. Rear cage. Again it is coming to the bottom headers, ring header. This is coming in dry mode. This is from cold reheat line. This is how the boiler works. Now we will come to how the feed water is controlled. Now in subcritical, that is power boilers, drum type boilers, 3 element control is there. We have much discussed on this issue also. Now in drumless boiler, that is supercritical boilers, the feed water is controlled by 2 means. One is water to fuel ratio and second is OHD, that is overheat degree. Now what is this overheat degree? You see in subcritical boilers, we observe that if there is very, very low water level, then boiler trips. But in this case, in the furnace, if the temperature increases up to 30 degrees centigrade, then the required one, then the boiler trips. And that temperature is called the overheat degree. So that is the protection for low water level. Now what is variable sliding pressure operation? This is very important in this boiler. In our boiler, in subcritical boilers, power boilers, we have observed that depending on the load, that is full load or part load, how the throttling of the steam is taking place in the turbine. So that type of throttling is not taking place in the supercritical boilers. Now we will understand by reading this how it takes place. Now steam generation at supercritical conditions ensures high efficiency at full load. Then it must be complemented by variable or sliding operation to obtain good part load efficiency and dynamics. Part load efficiency, that means even for part load there should not be a drop in the efficiency. That is the concept behind that. Then steam turbine demands lower inlet pressure at lower loads. Conventional drum type boiler generates steam at constant pressure. Pressure is then reduced in the main throttle valves to feed the nozzles at suitable lower pressure. Then this is not always the case, and drum type boilers are also designed for variable pressure operation, and that is particularly with the help of assisted circulation. That means in case of assisted circulations, there may be a sliding operation also. with fixed drop in the throttle wall is a waste of energy. And this wastage of energy is avoided in this supercritical operation, which increases as load reduces. That wastage of energy also increases during the reduction in the load. That is avoided. More efficient system would generate steam at lower variable pressure instead of generating steam at higher pressure and killing in the throttle wall. The throttle valves and the main stop valves could be dispensed with, and the speed of the feed pump could be varied to suit the inlet pressure of the turbine. That means there is much saving in the auxiliary consumption of the feed pump. So this is called the variable pressure operation. And the boiler operates on this concept. Now in figures we will see that as per the load, main steam pressure, how it is varying with this concept of sliding pressure operation. As the load increases, you see the steam pressure, how it increases. And if it is a fixed pressure, then it is a constant one. Now in the second figure, we see how the load increases corresponding to the percentage of feed pump auxiliary power, that is consumption of the feed pump. That is very important in these supercritical boilers, consumption of the feed pump. It has to work with maximum power, and that could be saved. Now water wall arrangement, as we have discussed, bottom spiral and top vertical tube furnace arrangement. Then supercritical water wall is exposed to the high heat flux. Spiral tube wall design wrapped around the unit with high mass flow and velocity of steam water also. Then higher mass flow improves the heat transfer between the water wall tube and the fluid at high heat flux. Now this is the comparison between spiral and vertical wall. Then in vertical wall, there is a less ash deposition on wall, less mass flow, more number of tubes. In case of vertical wall, that is plain tubes. Then no uniform heating of tubes and heat transfer in all tubes of water wall. Correspondingly, spiral wall, there is a more ash deposition, external, more fluid mass flow, less number of tubes, less boiler height, and uniform heat transfer and uniform heating of water wall tubes. Now this is the reason why right from beginning, from bottom, the plain tubes are not used. You see, up to the bottom half portion of the furnace, the tube construction is inclined, that is at 30 degree. That is 30 degree helix starts from the bottom header and it ends at the top of the bottom furnace. Now this is the comparison of supercritical and subcritical boilers. Important is circulation ratio. Then subcritical, that ratio may be up to 7 to 8 also. Feed water flow. The water to fuel ratio OHD, that is over degree, is up to 22 to 35. That means if the temperature rises from 22 to 35 degrees centigrade, the boiler trips. Then there is a 3-element control. Then latent heat is nil. Their heat absorption is more. Specific enthalpy is less. Subcritical more. Specific coal consumption. This is very important. Why this technology has come up? This is one of the answers in that. 0.6 kg per kWh, and there is 0.68 kg per kWh. The difference is lot because you see million tons of coal we are using there. So that is a saving of fuel. Then coal and ash handling capacity low, there is high, pollution low, high, auxiliary power consumption low, overall efficiency is up to 40 2 degree centigrade, 2 degree percent, 42%, and low is 36 to 37. So in some cases, now the boilers are even running on advanced ultra supercritical. What is meant by advanced ultra supercriticals? They are running up to even 400 bar and 750 degree centigrade. In that case, the efficiency is even up to 50%. Then blowdown loss is nil, but up to 30% load, there is a blowdown. Water consumption is less. Now regarding the material, you see the materials are very high, that is alloy steels, high chrome, moly. But if for economizers, they are just carbon steel, and welding joints are more for supercritical boilers, that is almost double. Now, this is one of the advanced supercritical tube materials where the boiler is working up to 300 bar and 620 degree centigrade. So this is high grade alloy steel. Then steam water cycle chemistry is also very stringent, you can see. You see the time restriction they have given me, but I myself will extend this, because basically it is difficult to understand. Again, time is limited, that is restriction. So anyway, yes. Even then we have to run. Okay. That is basically, I will understand this. This all volatile treatment that is done by hydrogen and ammonia, this is very important. And the second aspect of this treatment is CPU, condensing polish unit, condensing polishing unit, that is external treatment. There is no internal treatment in this type of technology. Now, what are the advantages? Higher cycle efficiency means primarily less fuel consumption. Per megawatt infrastructure investment is low comparatively. Less emission, less auxiliary power consumption, less water consumption. Then operational flexibility is more. That is better temperature control and load change flexibility. More suitable for widely variable pressure operations. Now, what is the economy? The economy is in fuel and all operation activities. Now, this is very important. Approximate improvement in cycle efficiency, how it is increased. That means 0.005% efficiency increase per bar if the pressure is increased by 1 bar. So, you multiply that to this 0.005, you will get the result. Now, the temperature increase, 0.011% efficiency per degree centigrade. Now, this is the scenario how the pressures were increased along with the temperature and how the efficiency is raised during the development of this technology. Now, what are the challenges? Water chemistry is very important challenge for this. Then metallurgy, then more complex reaction. Maintenance of tube leakage is difficult. Then ash sticking tendency is also more. Now we will come to the present scenario of the electricity in our country. First we'll see in Maharashtra. Then what are the supercritical units working in Maharashtra state? 3 into 660 megawatt Koradi, Mahajanko, make is L&T. 1 into 660 megawatt Bhusawal, Mahajanko, BHEL. 2 into 660 megawatt Mauda, NTPC, BHEL. 2 into 660 megawatt Solapur, NTPC, that I have wrongly written there BHEL, but I think it is Hitachi. Okay. 5 into 660 megawatt Tiroda, Adani Power, that is Shanghai boiler make. Then proposed supercritical units in Maharashtra. 2 into 660 megawatt Koradi, Mahajanko, again BHEL. 1 into 800 megawatt Paras, Mahajanko, BHEL. 1 into 660 megawatt Chandrapur, Mahajanko, BHEL. 1 into 800 megawatt Bhusawal, Mahajanko, BHEL. Now Maharashtra load demand. आपली load demand काय आहे? At peak hours load demand is 29,500 megawatt. Lowest demand is 23,000 megawatt. Now what are the top 10 thermal power plants in India? Whenever we are discussing why supercritical technology, you will get the answers of this question in the last situation. Now top 10 you can see Madhya Pradesh 4760 megawatt NTPC BHL, Adani 4620 megawatt, Adani Shanghai Boiler Works, then Tata Ultra Mega Power Gujarat, that is at Mundra 3960 Reliance Shanghai Boiler Works, Tiroda Thermal Power Plant Maharashtra 3300 megawatt Adani Shanghai Power Works, then Talcher Super Thermal Station Odisha 3000 megawatt NTPC BHEL, then Rihand Thermal Power Station Uttar Pradesh 3000 NTPC BHEL, Shipat Super Thermal Power Plant Chhattisgarh 2980 megawatt NTPC BHEL, Chandrapur Super Thermal Power Station 2920 megawatt Mahajanko BHEL, then Dadri Thermal, that is 2637 megawatt, that is of NTPC. This is the situation of 10 thermal power plants in India. Now India's electricity generation and capacity, म्हणजे आपल्या भारताची installed capacity till 2025 is 5,09,740 megawatt. Then maximum demand is 2,42,490 megawatt. And the grid capacity, existing grid, that means to carry the electricity generated, is 5,70,000 megawatt. This is inclusive of subcritical and supercritical boilers working today. Now the conclusion is that higher efficiency and lower emission to adopt this technology. This is the reason. Then design, once through design, the components, there is no steam drum and weight calculations are done compared to subcritical. Then better heat transfers are observed in this technology. Then there is improved flexibility, that is once through system also, flexibility of operation. And I think the answer of this question, today's lecture, why supercritical technology, I hope all of you may have received that. So this is, thank you.
Thank you, sir. Thank you, sir. In case if any query? आता बहुतेक कोणी मूडमध्ये नाही आहे काही प्रश्न विचारण्याचा. ओके, कारण एक अख्खा दिवस खूप काही ऐकलंय आणि ते आता आधी डायजेस्ट व्हायला पाहिजे प्रॉपर, की आपण आज काय नवीन किती शिकलो ते. आणि नुसतं शिकायचं नाही आहे ना, आपल्याला इथून जाऊन आपापल्या ठिकाणी ते इम्प्लिमेंट पण करायचं आहे. सो फर्स्ट ऑफ ऑल थँक्यू व्हेरी मच श्री GT चौगुले साहेब. मी आदरणीय श्री UN पाटील साहेबांना विनंती करते, आपण साहेबांचा सन्मान करावा. म्युझिक द्या ना. here we conclude the last session, and here we conclude the first day of safe and efficient use of boilers, a awareness program and the seminar organized by Joint Director of Steam Boilers, Pune. मंडळी, यानंतर मी बोलणार नाही काही, म्हणून एक सूचना, आत्ताच इथून निघताना आपण आपापले पार्टिसिपेशन सर्टिफिकेट्स गेटवरून घ्यायचे आहेत. थँक्यू सो मच. अँड हिअर वी एंड अप टुडेज डे विथ स्टेट अँथेम अँड फॉलोड बाय द नॅशनल अँथेम.
महाराष्ट्र माझा गरजा महाराष्ट्र माझा जय जय महाराष्ट्र माझा गरजा महाराष्ट्र माझा भीतीनं आम्हा तुझी मुळी कडकडणाऱ्या नभा अस्मानाच्या सुलतानीला सबाब देती जिभा सह्याद्रीचा सिंह गर्जत शिवशंभू राजा
दरी दरीतून नाद गुंजला महाराष्ट्र माझा
जय महाराष्ट्र माझा गरजा महाराष्ट्र माझा काळ्या छातीवरी कोरली अभिमानाची लेणी
ओलादी मनगटे खेळती खेळ जीव घेणी
दारिद्र्याच्या उन्हात शिजला
निढळाच्या घामाने भिजला
देश गौरवासाठी झिजला दिल्लीचे ही दस्तराणी तो महाराष्ट्र माझा जय जय महाराष्ट्र माझा गरजा महाराष्ट्र माझा जय जय महाराष्ट्र माझा.
राष्ट्रगीत शुरू करेंगे. शुरू कर.
नायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंग विंध्य हिमाचल यमुना गंगा उच्छल जलधि तरंग तव शुभ नामे जागे तव शुभ आशीष मागे गाहे तव जय गाथा जनगण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे.
भारत माता की वंदे वंदे. थँक्यू सो मच.